Hi, Kyle.
Hey, John.
Right? Stupid Band-Aid.
Oh, yeah, sorry. One second.
Thank you.
Sorry, I don't know if you can hear me among all the commotion. There's school just got out, so there's a lot of people coming in. Hang on, I think I might have to fix my audio because I'm not hearing you. 1 second.
Can you hear me now?
Oh, yeah, I think I just have my volume down too low. Well, I don't know. I did hear you just then. All right, I think we're working. So I've been telling people we would start around 3:30, so I just want to give kids some time to filter their way down here. So I think we're planning on like a 30-minute talk followed by Q&A. What do you have going on?
I sent it.
Oh, okay. Well, you can always just like stick around for what you can, and then if you have to leave.
Okay.
So either right now or before you want to like write your names on this, just so that like you know who attended and stuff like that.
So I've left everybody.
And like while you do that, you can also grab them.
I don't know what I want.
It's been a hectic day.
Yeah. In here.
So how are things going at IU?
They're going well. I think the semester's been off to a reasonably good start. Some complications, but mostly.
That's good. We're actually in our homecoming week. We're supposed to wear college stuff today, and apparently my red Indiana shirt is missing. So I have my Science Fest shirt from 2017. That was the best I could do.
I should have worn mine.
Maybe that's acceptable. I think 2017 might be the last time I've been to Science Fest. It's kind of sad. Is that happening? Is that happening just outdoor only this year? Is that what I saw?
Here, outdoor only.
Okay. Did it happen at all last year?
I don't,
Okay.
Really?
And as you're waiting, you guys can join the remind either now or by the end of the session. Because that's usually where I post my updates and stuff. So I'll just write the code up here. Yeah.
So I've just got you down on my computer now, but I'm gonna move the Zoom screen over to my projector now, if that's all right.
Mr. Hunt, can I
Yes.
just ask you things
Oh.
as you're getting set up?
Sure.
Okay, so I mainly will be using Remind to kind of announce these sessions. So you guys can either use you can use the text version or the actual Remind code. It's this, and join the Remind, please. And also, one thing that we've introduced is that during the session, if you take some notes maybe, and please be prepared to ask some questions at the end of the session. We will have a Q&A part. And later after the session at home, before the next session, if you write a little summary or if you write what you took away from this session, we will be able to post that on the website. So do contribute to that. So for attending each session, you will receive 10 points, and people who write a little summary will receive extra points. And the people who get the most points at the end of every 2 months will be mentioned specially on our website. So that makes sense. Thank you guys for showing up though.
Okay. So I think we're just about ready. Would you like me to give you a brief intro, John?
whatever you like, I can just start talking. But if you want to say a few words, that's fine.
All right. So is everybody able to hear all right? Okay. So I'll just read a quick bio that was sent to me. So our speaker today is Dr.Jon Urheim. He's a member of the physics department faculty at Indiana University. He's been there since 2003. He has degrees from MIT and the University of Pennsylvania. He held a postdoc position at Caltech and a faculty appointment at University of Minnesota. His area of research is high energy particle physics. And then he has worked on experiments at accelerator facilities at places like Brookhaven Lab, Cornell University, which is in New York, Fermi Lab in Chicago, and CERN, which is it's the Center of European Nuclear Research, if I have that acronym more or less right, in Switzerland. He's worked on things related to quark and lepton flavor structure of elementary particles. And it also includes the studies of mesons containing heavy quarks, tau lepton physics, searches for rare and forbidden processes, and measurements of neutrino flavor oscillations. So I'm sure all of that sounds a little bit esoteric to a lot of you, but it's very cool particle level physics stuff. Kind of centers around the search for the fundamental particles and forces that sort of make up everything. And then Dr. Urheim lives in Bloomington with his wife, also a physics professor at IU, who also happened to be my PhD advisor, and 2 children. Right, so take it away, John.
Okay, well, hi everyone. It's a pleasure to be here. I think I can see some of you, so thanks again. I'm going to show some slides, and please feel free to interrupt if you have questions as we go. But hopefully, the presentation will be short enough that we can have sort of question and answer afterwards. So I'm going to share my screen. So Kyle, you have to let me.
Oh, yeah, sorry. Sorry, I know I can do this. This before, how do I do this? I just have to allow him to share screens. Oh, it's share screen. Okay, there we go. You should be allowed to now. There we go.
Yes. Okay, so, you know, I worked in experimental physics in a particular corner of experimental physics. I'm going to try to put that area in a little bit of perspective and maybe also give you a little bit of an idea of what sorts of things we study, you know, sort of drawing from things that I know as well as some of my own experiences. What sort of work we do. So what I will first try to do is break down a little bit where my area of research sits within, you know, the pantheon of the sciences, but also within physics. And then, like I said, give some examples. And so, you know, a couple of examples from my own experience. Physics done at accelerator facilities where it collide beams of electrons and positrons. Positrons being the antiparticles. And then also what I work on currently, which has to do with the phenomenon of neutrino oscillations. And I'm not going to be able to go into a lot of detail. I'll also say that a lot of this is sort of infused with some amount of jargon and discussion of concepts that, you know, I'm sure many of you, know nothing of. Maybe you've heard some of the words before. So I'm not going to try to explain things in great detail, but just give you a flavor. Hopefully, in the course of doing this, I'll be able to tell you a little bit about what doing research in this area is like and what the outlets are. So first,
Hey, John, sorry, can I stop you real quick? We're having some issues with the audio over here. It's a little choppy. I might just have to get my settings fixed over here. I've got a couple of different volume controls here that I'm kind of fiddling with, so apologies for that. I might have something turned up too high and something else turned down too low. I'm not sure. Right. Go ahead and try to say something now. See if it's coming in better. So, John?
can you hear me?
Yeah. Does that sound better? All right. Is everybody able to understand all right? Okay. I think it might be a little bit better now. Sorry about that. I'll mute myself again.
Okay, so I'm going to continue. And again, just as a way of orienting people, of course, physics, if you like, sits at the bottom of the pyramid of sciences in many ways. If you look at scientific and engineering disciplines, many of them draw from physics. Certainly, physics informs the way biology works, informs our understanding of astronomy, formation of stars and planets, and so forth. And the universe itself, for that matter, things like atmospheric science, geology, chemistry, why chemistry works, is ultimately physics. Of course, many things of engineering, including electronics. So, within physics, of course, it's a broad array of subdisciplines. I've just listed a few here, some of the main ones: astrophysics, chemical physics, biological physics, condensed matter physics, atomic and optical physics, nuclear physics, and elementary particle physics. And if you go further down the chain, and so let me just expand, for example, to that's matter physics. That's an area that has to do with properties, behavior of materials that are comprised of collections of atoms or molecules. So, a wide range of phenomena are present in these materials, including everyday conductivity, why electric charge flows through wires, for example, including how materials that are called semiconductors work, which are very important for our electronics industry. Things like superconductivity, superfluidity, all manner of material science. Many universities have departments outside of physics that are material science departments, but essentially they're nanomaterials is a popular area now as people have understood how to fabricate material structures at just the sort of few atom thickness scale. There are a number of very amazing properties of these materials. So that's just to give a little bit of an example. I don't work in condensed matter physics or any of the other ones listed, except for the one at the bottom, which is elementary particle physics. So when you get into physics research, you do find that you end up specializing in some way. So although I have some familiarity with all of these fields, my bread and butter working knowledge is. So to take you through that, let me just say that, of course, what we think about when we think about elementary particle physics is subatomic physics. So properties of particles, forces at the subatomic scale. So what does that mean? Well, we know atoms, right? We know atoms are comprised of atomic nucleus with a sort of cloud of electrons. So that's in chemistry, have some appreciation for the idea of electron orbitals, how the electrons are arranged according to the laws of quantum mechanics. We think that the electrons are point-like particles. As far as we know, they have no internal structure, but the atomic nucleus does have a structure. It's made up of protons and neutrons, which for many years were thought to be fundamental particles, indivisible. But indeed, work over the past 40 or 50 years has demonstrated that within the protons and neutrons is some structure, and that structure is described by smaller particles that appear to be point-like, which we call qubits. Okay, so that's sort of going down, if you like, through a microscope from macroscopic down to very small. And within particle physics, we have something called a standard model. Standard model is, the word model is kind of a funny thing here. The standard model is a very sophisticated theoretical description of subatomic particles and how they interact. It's very successful. Predictions from the standard model have been tested at very high levels of precision. Wide array of experiments. And that standard model arranges the particles and in particular, the particles that make up matter, as well as the particles that imbue matter with interactions, the particles that are responsible for forces, into something like a periodic table. But this is not a periodic table of atomic elements, it's a periodic table of particles that we think are fundamental, are indivisible, at least to the extent that. And those particles, and I know probably many of you have encountered this sort of pictorial representation of how to think of these particles. They divide into several types. So we have sort of the three families, three generations of matter particles. And of those, there are basically two types. There are so-called quarks, so-called leptons, where the distinction between the quarks and the leptons is that the quarks carry a type of charge. In addition to electric charge, which they also carry, they carry a charge that makes them susceptible to what we call the strong interaction, which is only operates on very short distance scales, subatomic distance scales. Whereas the leptons, which have electrically charged ones, for example, the electron is the lightest of these, but also neutral ones called neutrinos, these are impervious to the strong force. And so that makes their interactions qualitatively different. Now, the particles that we see in everyday matter are really just three types. There's the up quark and the down quark, which in different combinations form protons and neutrons. And the electron, of course, the atoms have electrons for other things. What we find is that, and these are part of what we call the first generation of these particles. What we find is that the second and third generations of these particles are essentially heavier cousins of first generation. And in all ways, except for the fact that they're heavier, they behave or are observed to behave exactly the same way. By virtue of the fact that they're heavier, they also, it turns out, are not stable with decay and into lighter particles. And so we don't really see them too much in nature. We have to go to accelerators or high energy cosmic rays. In addition to those, quarks and leptons, we also have these things called gauge bosons, which are very forces. And there is this what we call the photon, which is typically the carrier of the force responsible for photons. And then there's another type of particle that was recently discovered that you may have heard of called the Higgs boson, discovered at CERN in 2012. This particle is believed to be responsible for giving all of these particles. And the standard model particle physics is a very successful theory, but there are a number of what we call free parameters in that theory. In other words, the standard model doesn't tell us why there are three generations. It doesn't tell us why these particles have the masses. It doesn't tell us a number of other important properties about them that we observe in experiments. So we believe that actually there's something that goes beyond the standard model. Help explain something seemingly arbitrary. So that's sort of a theoretical characterization, this periodic table of particles. I'm an experimentalist, which means that I work on trying to make measurements. And there are physicists who specialize in that. But there are also physicists who specialize in trying to understand the observed phenomena, characterizing them from theories, trying to deeper understand why. And so I like this quote from Yogi Berra, who was a well-known baseball player in the 1960s. And he said a lot of very interesting things that I think really have to do with physics. And one of the things he said was, in theory, there is no difference between theory and practice. Practice there is. And so I'll try to give you a little bit of a flavor for that, where by practice I mean experiment. And so now I'm going to talk a little bit about experiments. And I'm going to show you on the next slide what I think is the most famous of all time of pictures in experimental particle physics. And it goes back quite a ways. It goes back to 1964. That is a photograph of bubbles in a vat of liquid hydrogen that record the passage of charged particles. Charged particles that are produced in interaction of a beam particle from an accelerator ionizes the water molecules, or the hydrogen atoms actually, in this bubble chamber, and causes the formation of bubbles. And so you can record, and so here it is. You can record the trajectories of charged particles by looking at the pattern of the bubbles that are formed, and a photograph is taken. Now, this is a very difficult to work with detector type because you have to constantly be pressurizing and depressurizing the vat of hydrogen, and you have to take a picture at just at the right time. And you can only do this so frequently. So you have to be very lucky to see something interesting. And in fact, this is a photograph that corresponds to the first recorded production of something called the omega minus baryon, which is like a proton, in the sense that it's made up of 3 quarks. The proton is made up of 2 up quarks and a down quark, but the omega minus particle is made up of 3 strange quarks from that second generation. If we go back to here, so here's the strange quark here. So it's a very interesting and exotic particle. It's only produced by virtue of the fact that there was a tense beam of protons that was slammed into some solid material, and some particles emerged from that, including something called a negative kaon. And that negative kaon traveled into this bubble chamber, leaving a trail of bubbles, recording its trajectory, and it struck a proton, a hydrogen nucleus, and that reaction led to the production of this omega minus and a bunch of other particles. And so if you look over here at the actual photograph, you can, it's busy because there are many other particles traveling through at the same time. But this negative kaon, K particle, that you see over here, and then there's sort of like a little kink, and then another kink. So this small segment of bubbles actually corresponds to the travel of this omega minus baryon K into some other particles, some of which were electrically charged, so led to more bubble formation, such as this one here, but others which were electrically neutral, so were invisible. So this gives you, I think, a feel for the sort of thing that we try to do in experimental particle physics, is we try to create particles through collisions. We try to visualize the interactions by recording signals from the detector. In this case, they're visual signals because we're looking at bubbles, but in more modern day detectors, we're looking at electronic signals from detectors where essentially collect the ionization electrons or data in some format from sensitive to those electrons. Okay, or light, particles of light. Okay, so that's to give you a little bit of a flavor for experimental particle physics. And what I want to do now is maybe just spend a couple minutes, again, giving you kind of a flavor for some more modern types of experiments. And I'm going to start by talking about experiments that look at collisions of electrons and positrons. And as I said, we think of electrons as being point-like, and so are the positrons. Electrons are electrically charged, so we can control their trajectories and accelerate them using magnetic and electric fields. And we can generate beams of electrons and positrons and bring them into collision. One common way of doing this is to have what we call circular accelerator, something like this depiction here of something called LEP, which is the Large Electron Positron operated at CERN in Geneva some time ago. And essentially, that accelerator consists of a ring that's 27 kilometers in circumference. That's about 70 miles in circumference. So a tunnel was dug underground, under Geneva, essentially. I'll show you a photograph in a little bit. And magnets were put in this tunnel in the magnetic field, charged particle trajectories are bent. And so let's bend the trajectories of the beams of particles into a circle, and then the two beams are brought into collision at various what we call interaction points. Okay? And at 4 of those interaction points, we'll place very large, capable suites of detectors. So here's a picture of Geneva. Okay, it's right on this is at the CERN laboratory, which is right on the border between Switzerland and France. Part of it is in Switzerland and France. Over here, and, airport. This is farmland around here, and you can see inside the tunnel. These structures here are some of the magnets that bend and focus. And at these interaction points are sited very large detectors, which are constructed by large teams of scientists and engineers, with also partners from industry. So this is an example of one of those, the owl detector. And the detector essentially looks like a big cylinder, okay, but with lots of stuff inside. So this is a cutaway view. The positrons come in from the left, the electrons come in from the right, they collide in the middle, and they produce particles which then can travel through the active material of the detector. So this is a schematic representation of this. You see the size of the scale. Here's a photograph of sort of one of the end cap portions pulled away from the sort of inner barrel part, which is here. Now, an interesting thing is that when you have a beam of positrons and colliding with a beam of electrons, a positron can interact with an electron through a process called annihilation. That's not the only way it can, but that's what happens. And when that happens, normally, in order to conserve momentum and energy, you produce some number of particles in final state. You tend to produce particle particles. And one of the great things about working with particle physics is I get to work with Einstein's famous E equals mc squared equation all the time. Basically, this is saying that there is an equivalence between energy and mass. So any object, any particle that has some mass, has some energy associated with that mass. And so if you want to produce, through annihilating an electron and a positron, which are very light particles, but accelerate at very high energies, you want to produce a pair of heavier particles, you have to have at least as much energy in each beam particle as the mass of the particle that you're trying to produce. Okay? So one possibility is that an electron, positron will annihilate and produce a muon and an anti-muon. Muon being like a heavy cousin of the electron. Okay? And so you have to have enough energy to produce that muon because the muon is heavier and therefore to conserve energy in the final state has to have at least as much energy as twice the. So the energy to which the electrons are accelerated, each of them has to be at least the energy that corresponds to this. And similarly for the other particles, which get progressively heavier. Any questions so far? Okay, and so I'm going to show this plot, and there's a lot going on in this plot. I'm just trying to give you a flavor for this, and I'm not going to spend much time on it, but please ask me if you have questions afterward. On the horizontal axis of this plot is the combined energy of the an electron in the electron beam and the positron in the positron. Okay, in units of giga-electron volts. Which is the unit of energy. It's also a unit of mass. And this is a logarithmic scale. So this is 1 GeV here. That corresponds to the mass of a proton. 10 GeV. And when this is plotted on the vertical axis, also on a logarithmic scale, is essentially what we call the cross section, which tells you the rate, the probability of those that electron and that positron colliding and producing some final state. And you can see that it's an interesting plot. There's a lot of stuff that's going on. And so what I said is that you could have, for example, an electron and positron annihilating, producing a muon and an anti-muon that come out. And that's not a very interesting process. But if you produce a quark and an anti-quark, well, if you have just the right amount of energy, so that quark and anti-quark coming out have no kinetic energy. In other words, all of the collision energy goes into the mass of that quark anti-quark pair. Then what happens is that the strong interaction for the quark and the anti-quark can move away in a sense. For that to happen, the strong interaction exerts a force between those two that leads to a bound state, very much like the hydrogen atom, proton and electron. But the force that's binding the electron to the proton is electricity. It's the electrical force. Whereas in this case, it's what we call strong force. And just in the same way that for a hydrogen atom, you can have the electrons in different orbitals. You can also have, this quark, anti-quark bound state be in different kinds of orbitals, if you like. And those different states with the different orbitals actually corresponds to different particles. In other words, the energy difference between those states is so large that you think of it as, well, one, quark, anti-quark orbital, if you like, corresponds to a particle with a certain mass, and then another one that's a more energetic state has a higher mass. So sometimes you see evidence for production of these particles that are quark, anti-quark bound states. For example, this thing called the J psi is a bound state between the charm quark and the anti-charm quark. That's one of them. The psi 2s is another orbital of that charm anti-charm quark pair, so on and so forth. This thing here is direct production of a single particle, the Z boson. So the Z boson is one of the carriers of what we call the weak force, along with the W boson. And it's very heavy. It's about 90 times the mass of the proton. But if you accelerate the electron and positron beams to exactly each one being 90 GeV, then you can produce this single particle with no kinetic energy at rest. And you see a huge enhancement for production of this particle, which very rapidly decays to final state. And so, just to give a flavor, there's a lot to study about this, including not just the peaks, but also you see little shifts as you go along in the overall level, which the peaks sit. I worked on an experiment that was at lower energy than the one at CERN, called the Clio experiment, which operated at Cornell. And that operated at this region here around what we call center of mass energy. So each of the beams is 5 GeV of energy. And we did a lot of physics with that. Here's an example where the electron and positron annihilated to produce a heavier version of the electron positron, not the muon anti-muon, but simply called the tau anti-tau particle. Go back to here. That's this guy here. And the tau has a mass of about 1.7 times the mass of the proton. And what happens is that this is sort of an edge-on view of the detector. So the positron beam is going into the page, and the electron beam is coming out. And they annihilate in the center and produce a tau particle, a tau plus and a tau minus particle that go back to back, but in some direction that's not along the beam axis, but some other direction. And so presumably one of them went this way and the other one went that way. And you see some activity in the detector that corresponds to charged particles that tau particle decayed into, as well as electrically neutral particles. So studying these types of events is what they mean, how to interpret them is is a lot of the sort of work that I've done. I'm going to skip this in the interest of time and just start to give another example of something that I work on now, which is called neutrino oscillation physics. And this has to do with neutrinos. Neutrinos are these electrically neutral particles that are very light. They're leptons, so they don't feel the strong force, and they're not electrically charged, and they have no internal structure as far as we know, so they don't feel the electric or magnetic forces either. And so there's something called the weak force that they do feel. And we talked about these W and Z bosons that are the carriers of that force. But as the name implies, that those interactions are very weak. They won't happen very frequently. And so neutrinos are interesting to study because they give you a window onto this without interference from electromagnetic strong interactions. Because they're electrically neutral, unlike the other fundamental particles, or fundamental matter particles, it turns out that they might actually, and we don't know this, be their own antiparticles. Or there might be separate types of particles that are antineutrinos that are distinct from neutrinos. Understanding this is a very important question. Again, there are three types of neutrinos. One that corresponds to the sort of partner to the electron, one that's a partner to the muon, and one that's a partner to the tau particle. Again, why there are these three flavors or generations, we don't know. Why there are corresponding number of generations of quarks, we don't know. It also turns out that there's some weird property where if you let, say, an electron neutrino travel over some time, distance, that when you try to detect it, it interacts not as you would expect an electron neutrino to interact, but rather as either a muon neutrino or a tau neutrino. And this is what's called neutrino oscillation. It's a very surprising property. It's made possible by quantum mechanics, but you can learn a lot about standard model particle physics by studying these things. And in particular, one of the free parameters in the standard model particle physics is something we call a phase angle that allows for the possibility that particles behave differently from each other. And we know that there has to have been, at least in the early universe, some distinction between particles and antiparticles, because our universe is made up of photons and neutrons and electrons, and not equal mixtures of those corresponding. So why there is this asymmetry is a big mystery. And it may be that the neutrino oscillation. Now, in order to study this neutrino oscillation phenomenon, you have to let the neutrinos propagate, so they have time to oscillate. And for sort of energies of interest, you actually have to let them propagate for a long time. It's a long distance. So the types of experiments that I work on are these things called long baseline neutrino oscillation experiments, where you have a source of neutrinos, and the source that I mostly use at Fermi National Accelerator in Chicago, and we generate beams of those neutrinos that are sent essentially through the Earth to various locations where there are detectors, which can detect a very small fraction of the neutrinos. Small fraction because the weak interaction is so weak that most of the neutrinos travel through the Earth to get to their source, to get to where the detectors are without interacting, and most of them go through the detectors without interacting. It's only a very, very small fraction. And I've worked on 2 experiments where the detectors have been located in northern Minnesota. One that's deep underground in air mine called Minos, and another one that's located on the surface in the town of Ash River, Minnesota. Working on another one that's in preparation called Dune, where the detectors will be sited in South Dakota. So neutrinos are traveling all the way from Chicago to this. Just to show you what the accelerator facility at Fermilab looks like, there's an aerial view of the Fermilab campus, and sort of the main accelerator complex starts over here with a smaller accelerator that feed into larger accelerators, including this one called the beam ejector, which accelerates photons to an energy of 120 G. And those photons are extracted, they collide into a target, which produce other particles that, as they travel, decay into final states that include neutrinos, and then those neutrinos. Because again, you need a lot of matter for the neutrinos to interact with to get an appreciable event count. If they interact so rarely, the detectors are very large. So what's shown here schematically is a depiction of what we call the NOVA detector, which is 14,000 tons of plastic polyvinyl chloride cells fabricated by companies that make garage doors, actually, into which we pour liquid cinnamon, which is mostly mineral. So together, the 4 million gallons of mineral oil represents about 10,000 tons, and then the additional mass comes from the detector structure itself. And, lots of glues used to put all of this together, but this is sensitive to neutrinos, and we're taking data with it now. If you come to IU, you can visit us and see a control room where we actually monitor detectors. This just gives a sense of how the scale, just how large this thing is. This is looking from the top of the detector completion. We also have a smaller version that's on the Fermilab site that helps us calibrate. Just to show you some people of the, some picture of the scientists who work on this. I want to mention that, in physics, especially in a very collaborative field like particle physics, where you need a lot of people to come together to make a large, complex experiment work, you get to meet many interesting people from all over the world, and it's a very interesting. Just to give a flavor that this oscillation phenomenon happens, this is a plot of the number of neutrino interactions that we see as a function of the energy of the neutrinos that we record. And what we see for those numbers are shown in these black points, a number that we would expect if we didn't have neutrino oscillations in this blue part. So it turns out that most of the neutrinos produced at Fermilab, by the time they get to northern Minnesota, they oscillate, they change into a different. Okay. I'm working on a next generation experiment called DOOM, where the detector technology is not liquid scintillator, but rather liquid argon. So that operates at cryogenic temperatures, and one gets exquisite pictures, just like the bubble chamber pictures, if you like, but without all of the hassles of the bubble chamber, of the interactions of a neutrino. Neutrinos are electrically neutral, so they come in, say, from the left here. You don't see any signature until they actually interact. And then you see the trajectories of the charge particles. And what we do is we have this beam of photons Fermilab that are slammed into a target, and we have the small version of the beam detector located, or will be located on the Fermilab campus. But most of the neutrinos travel through that, through the Earth, to reach South Dakota, where we have 70,000 tons of argon, and then those neutrinos continue, most of them continue on. And just to say that, when we contribute to these experiments, although we're working with a very large group of people, a lot of what we do is done in small groups. So this is just a few photos of members of my group at Fermilab, including another faculty member who's now retired, and some of the detective development. So some of these photos are actually small labs, Fermilab, testing. Some of these prototypes, here's a sort of picture of this, have been installed into a large prototype for this moon experiment called Moon. That's located in the test beam facilities. So over here you can see a set of magnets that direct the test beam particles into this vessel that is filled with essentially 1,000 tons of water. Here I am inside this vessel, obviously before it was filled up. and with some of our detector modules, which are sort of like all like frames. That actually, after I left, and after everybody left, was filled up with liquid argon and we took some data. So I'm going to stop here and just summarize. My main points are that physics is a very diverse and challenging, the problems are challenging field of study. There are many open questions that are very interesting and many ambitious efforts at all scales, at small scales, medium scales, and large scales involving thousands of scientists working together to address these problems. And essentially, the training that you get when you engage in this type of research is problem solving. And usually it's asking, why is this piece of equipment not working? Why is this data looking weird? It's solving those sorts of problems. What I can say is that those are valuable skills that not just require some sort of technical knowledge, but also a lot of common sense, as it turns out. And what we find also is that a lot of the technology that we develop has real-world applications and spin-offs, and hopefully some of the science we do will eventually have some practical applications. Right now, it's basic science. But, there are a lot of contributions that we make into technology development, but also in training of students who go maybe not necessarily onto careers in physics, but go into industry and take what they learn about problem solving and some of the technical skills. I hope I've been able to give you a little bit of flavor for the kind of work we do in physics and particle physics. And thanks for having me visit you, and I'm happy to take questions. Kyle, you're muted, so I can't hear you.
Yeah, sorry, I was stopping. I was just polling the room first. So yeah, I think we do have some questions. So go ahead.
How long would you usually work on one project?
Oh, that's a very good question. So I'll tell you a story. When I was a graduate student, which was in the 1980s, late 1980s, that's to say, I worked on an experiment with about 20, 30 people. Stop. Sure. Between about 20 and 30 people, and the experiment was proposed in 1884, which is when it started. Built the experiment, built first parts of the experiment within a year or two, and something finished building it in the next year or so, and I had data from the full experiment that I used for PhD dissertation. I had that by 1988. So from conception to data, that was 4 years. I thought that was a long time. But nowadays, looking at the scale of these experiments, these very large experiments, such as the ones at CERN that I showed you, the neutrino experiments, from conception to data, it's decades. So now this is specific to my field. There are other fields that also have very long time scales. For example, some astrophysics experiments, especially ones that have to get launched on satellites, also take decades from conception to data. But many other fields, for example, condensed matter physics, biophysics. Dr. Hagner is familiar with biophysics. Those experiments are done on very short time scales. Typically, they don't require these huge pieces of apparatus. So it really depends a lot on the type of experiment. And there are even some particle physics experiments that are sort of tabletop, put together a few years. But as with anything, all the easy things have been done, or many of the easy things have been done. So to have a successful tabletop experiment, you have to have some really significant technical. So I don't know if that answered your question.
Yeah, thanks. I think we might be like starting to have some audio issues again. I don't know if it's like a gain thing, but I think when you're like talking softer, it's not picking you up quite as well. So it is like you were cutting out a little bit here and there times. So I think it's been freaking more or less. Sorry?
I'll try to talk loudly.
Okay, sorry. Yeah, I don't, it might just be a gain thing. But was there a question over here? Yeah, go ahead.
What kind of like degree or education would you
Wait, were you able to hear that, John?
No, I wasn't.
Oh, sorry. So the question was like what kind of degree or what kind of education would you need if you wanted to work with particle accelerators?
Okay. Well, that's a very good question. And what I would say is that there are some things that you can do with a bachelor's degree in physics. In fact, we hire sometimes undergraduate students here at IU to help us with the research. And there are jobs that maybe put you in contact with the science, but in a very specific technical role. For example, I know some students who, after they received their undergraduate degree in physics, have gone to Fermilab to work as operators for the accelerator facility. So they've got to sit in these fancy control rooms with all these adjustments to try to make the particle beams that are produced work as well as they can. It's a very challenging job, I can tell you that. But the people who fill that role oftentimes have just an undergraduate. To actually sort of participate in the science, I would say that you do need to have earned a PhD, simply because, as you can see, there are so many different aspects of what goes into doing the science. First of all, understanding the theoretical context, there's understanding the nature of the problems that you're trying to address with the experiments, there's understanding the technical aspects, whatever it is, cryogenics or electronics or particle detectors that you need to bring to bear to make the experiments work. That sort of training is what you get as a graduate student.
I actually kind of have a follow-up question to that. Can you give us any sort of sense, like maybe at IU in particular, do you happen to know, maybe off the top of your head, let's say, how many physics graduate students do you have? And of those, how many are working on particle physics? And of those, like how many would get a chance to spend some time, maybe at CERN or some other facility?
Yeah. So here in our department, we have about 100 graduate students, a little bit less at any given time. Of course, they graduate and new ones come in all the time. The time for PhD is not a short time. It's 5 or 6 years. It's a big commitment, but it's also a time when you can really focus on learning some really neat stuff, and working on a problem that is interesting to you. But I would say that of the 100 students that we have in our program, there's probably at any given time something like 20, 25 who are working with particle physics, and another 20 or 25 who are working in nuclear physics, which has a lot of overlap in science. And in my group on the neutrino oscillation experiments, where we have 3 faculty members working, right now we have 6 or 7 graduate students, all working in different ways. And like I say, there's specialization. There are some graduate students who come in and they really like computer programming, and so they help develop the software that allows us to analyze the data that we get. We have detectors that have essentially millions of channels, so large data sets, complicated calibrations, so that people who like to focus on that, there are people who like to focus on making the apparatus work. There are people who like to focus on doing R&D, research and development on detectors. and making prototypes and testing it. And so there's a lot of different activities that a graduate student can do. Sometimes students will engage in multiple of these activities. And then I would say about half of the students who receive PhDs in particle physics from our department go on to postdoctoral positions, either at universities or at one of the national labs, like Fermilab or Potato or Oak Ridge Lab, Alamos Lab, a number of labs, particle physics students done. And so one route for employment is to go to those labs and make scientific positions. And I would say the other half go into industry in some form or another. And what that means is, again, depending on what their preference, what they're interested in. Some students go into electronics development. Some students go into software and computing, dealing with large data sets, so data science. Some people go into finance, using some of the quantitative skills that they learn to quantitative modeling of finance. So it's a very broad array of options. And again, the sort of generic training of problem solving, quantitative analysis of data, quantitative reasoning prepares people very well for work in a wide range of fields.
Cool. Are there any other questions? I did have another one, but it was a bit more on the technical side. So are there no others at this point?
Do you guys have any questions about like what it's like working in a lab every day, or what it's like teaching? Maybe any general questions about what you do in graduate school, like any of that would be fun.
Yeah, Ron.
Like about how many hours a week do people of this career do?
Right. So the question was about how many hours a week do you spend on what it is you do? And I guess you could probably break that down by the different types of work that you do as well.
So, okay, well, I'm a university professor, and so significant part of that role is teaching. So I do teach physics courses, and that takes, even teaching one, I teach one physics course per semester. Even that takes a fair amount of time for preparation, course delivery, course material delivery. So, I would say that typically that's 15 to 20 hours a week. Teaching. And then I also have various service roles that I participate in, some that I'm assigned to and some that I do by choice. Those are very varied. It's hard to categorize those, but that's another 5 hours or so. And then the rest is I spend on research, and that's very open-ended. And it also fluctuates quite a bit depending on what stage of an experiment you're in, accelerators are running or not, what type of experiment it is, and whether we have deadlines that we're trying to meet as far as submitting proposals for funding or submitting papers to be published, things like that. And, so sometimes my weeks are very busy, and I stay up late nights and I work on weekends. That happens. Happened more when I was a graduate student, sort of the low man on the totem pole. Put upon a little bit more. But yeah, I would say it's not a 40-hour-a-week job. It's definitely more than that. On the other hand, you do get better at it as you go and get more efficient. So I've been doing this long enough that I can do it without destroying my personal life.
Yeah, I can relate to that a bit. I think my first year teaching here, I was probably working closer to 100 hours a week, or at least it felt like it. And now that's way down now. Cool. I actually, so I had kind of a technical question. The standard model is actually something that I have become interested in myself more recently. For anyone who is like, who thought some of this stuff was interesting and wants to know more about it, there's actually a really good YouTube channel just called Fermilab. There's a guy there named Don Lincoln who does a lot of educational videos. He talks a lot about the standard model and fundamental particles. I've actually watched a bunch of those videos. So one thing I was wondering about, you mentioned at the beginning that there are sort of 3 generations of matter, and each generation is sort of more massive than the previous one, requires more energy. And you mentioned that there's nothing in the standard model that necessarily predicts that there are just 3 generations.
That is correct.
So something I've wondered about is, do you have a sense for, if there were to be a 4th generation, is there any sort of prediction as to like what types of energies would be required to create those particles? And do we know whether our failure to see a 4th generation is just because our technology is currently inadequate to achieve those energies, or is maybe just the probability of seeing those particles very, very small? Or do you think that it just seems likely that there are only 3?
Well, that's a very excellent question. Elaborate on that. First, this question of why 3, it's a very good question. It turns out that this mechanism, this mixing, which is responsible for neutrino oscillations, you would not get this asymmetry between particles and antiparticles unless you have at least 3 generations, right? And so, there's something called the anthropic principle that sometimes people like to invoke to sort of help explain things. And I don't know what to think about it, to be honest. But the idea here is something like this: is we exist, we live in a universe which is all matter and no antimatter, right? And since the only way that could happen is if we have at least 3 generations, then that's kind of the explanation. So in other words, there's many universes interpretations where there's not just one universe, but many universes, and each universe, the laws of physics are a little bit different in some ways. We happen to be in a universe that does have 3 generations. Maybe there are other universes that have only 2. Maybe there are others that have 7. Right? But we're in 3 because if there weren't at least 3. That's the thing. Now, could there be more than 3? Sure, there could be more than 3. But here's a very interesting observation. So if I go to this plot here that I showed you, there's a lot of physics in this plot. If there were more than 3 generations of neutrinos, for example, then what we would see is that the width of this peak would be wider. Okay, so the width of this peak is inversely proportional to the lifetime of this Z particle. And if there were more neutrinos, then there would be more opportunities for the Z particle to decay into a neutrino-antineutrino pair. And that would decrease the lifetime and therefore increase the width of this peak. And the fact that the peak that we see this peak here is exactly as wide as we see it, strengthens the argument that there are only 3 families of neutrinos. Okay? So there are arguments like this that say that there are only 3. Now, for the Z particle to decay into a neutrino and antineutrino pair, the mass of the neutrino has to be less than half the mass of the Z to conserve energy. Right? So what happens if you have super heavy neutrinos that we haven't seen? Well, that could be. But what we know at least is that in terms of the generation of particles, generations of particles that we have access to. If there's a fourth one, the particles in that fourth generation have to be at least as heavy as half of the mass of this, which is pretty darn heavy. Could be, but and people look for heavy fourth generation particles. And there's an experiment, a set of experiments going on now. It's called the Large Hadron Collider, which is actually uses the tunnel for LEP. And they essentially added magnets so that they could accelerate protons, one beam of protons in one direction and another beam of protons in another direction to collide those protons. That facility is where the Higgs boson is. And the energies of those beams are 7 TeV. So not GeV, not 10 to the 9, but 10 to the 12 electron volts. And so far, there's been no sign of heavy fourth generation particles produced. So it's an open question, and maybe partially answered it to say that, well, if there are fourth generation, then those guys have to be really, really heavy. And why would they be so heavy? So I don't know if that answers your question.
Yeah, I think he gets there. It's just something I've been curious about for a while.
It is very interesting.
Right.
And, you know, the discoveries that have been made, you know, the tau particle, this one was discovered before any of these other ones were. And basically, it was discovered by a scientist working as part of a team who thought, well, maybe there should be a third generation. And he decided to look for, you know, something that would have the properties that this particle would have. And he actually found it. It turned out to be light enough that it was able to be produced at the electron-positron collider that it was working on. So sometimes you look and you find.
Yeah, I know some of these other particles were predicted to exist long before they were actually discovered. Was it the neutrino that went decades between when it was predicted and when it was discovered?
Yes, the neutrino, not in fact that there were 3 different types of neutrinos, but the fact that there was something called the neutrino was predicted in the 1930s by Wolfgang Pauli. First evidence for a particle with properties matching that of the neutrino, the proposed neutrino, that was in 1954.
So was that about 2 decades?
Decades, yeah.
Oh.
People were looking for the top quark when I was a graduate student, but it wasn't observed until really the late 1990s. So that went, you know, decades without being seen. And the Higgs boson was proposed also in the early 1970s, and that wasn't seen until 2012.
Yeah, I think I was just starting at IU when that was discovered. So in the time I started. All right, are there any other questions? All right, so I think that should do it for us. All right, thank you very much for joining us.
Yeah, my pleasure. Thanks, everyone. I'm going to.
Right. Actually, John, I think if it's all right with you, I think Sripado was wanting to just get a picture with you and the attendees here.
Hi, Dr.
Stop the share. Stop sharing.
Guys, we can just stand up here next to the screen, like take a picture.
It's weird with my Zoom.
All right.
Thank you, thank you. Thank you, guys.
You're welcome. Thanks for inviting me. Bye, Kyle. It's good to see you.
Thank you, Dr. Urheim.
Good to see you.
Good to see you. Thank you.
All right, I'll see you soon, hopefully. I don't know when we'll be in Bloomington again, but I have a week off coming up in a couple of weeks.
Thank you
So
guys.
maybe then.
Yeah.
Okay,
All right.
well, let us-
All right, take care.